Welcome back to the deep dive. So when you hear extended reality or XR mentioned, most people probably jump straight to the consumer stuff, right?
Yeah, things like gaming, maybe social media avatars, that kind of high-end entertainment.
Exactly. But focusing just on that, it kind of misses a huge part of the picture.
It really does, because the tech that's powering all those experiences, it's also building the foundation for some, well, radically different futures. High-stakes stuff.
Like secure industrial systems on one hand.
Right, optimizing factories, and then something completely different.
Hmm.
Ethical, community-focused, urban regeneration.
It's this technical race happening, behind the scenes that's just explosive.
Absolutely. We're not talking small steps here. It's basically a whole new slice of the global economy opening up.
You see the numbers the market hit, what, $27 billion recently?
Yeah, and the projections are just staggering. Over $209 billion in the next decade. That's a compound annual growth rate, a CAGR, of around 38.4%. That kind of economic pressure, it forces innovation, it pushes engineers to solve problems that, frankly, used to sound like pure science fiction.
And that urgency, that's exactly why we're digging into this today. Our mission for you in this deep dive is really threefold.
Okay.
First, we want to unpack the really cutting-edge optics,
Mm-hmm.
the stuff that makes seamless, comfortable AR actually, possible.
Then the security side.
Right. The intense, got to get it right, security needed for industry to actually use these tools. You hear the term Industry 5.0. This is part of that.
Hmm.
And finally, there's this amazing counter idea called the Paradise Project. It really tries to flip the script on how tech fits into society.
So we're basically charting two paths for spatial computing here. They're diverging quite sharply.
Yeah, one is laser focused on efficiency, profit, optimization.
And the other, it's centered on ethics, on community ownership, environmental healing.
Mhm.
It's a totally different goal.
Okay, so let's start by setting the scene properly. We kind of have to define the terms first, get everyone on the same page with this reality spectrum, or the virtuality continuum, as some call it.
Right. It helps to break it down. You got those four main acronyms floating around: XR, AR, MR, and VR.
XR first.
Yeah, extended reality, XR, that's just the big umbrella term. It covers basically any technology that mixes the physical and the digital worlds in some way. Just a handy label.
Got it. Okay, so at the, let's say, far end of that spectrum, you've got virtual reality, VR, probably the one people have known the longest.
Definitely. VR is that full immersion experience. You put on the headset, usually with near-eye displays or NEDs, and boom, the physical world is gone. Blocked out entirely.
It's incredibly effective, isn't it?
Oh, absolutely. You just have to look at something like the Walk the Plank demo to see its power.
Right, where people are standing on a solid floor, but they feel like they're on a narrow plank hundreds of feet up.
Exactly. And their bodies react. You see genuine, like, physiological fear responses, even though intellectually they know they're safe in a room.
Yeah, it's pretty wild.
It just demonstrates that high-fidelity VR, when it achieves that sensory coherence, it essentially generates reality for the human mind.
Okay, so that's VR. Moving back towards the physical world a bit, we hit augmented reality, AR.
Right. AR is where you start overlaying digital stuff onto your view of the real world. Think of those simple Snapchat filters, maybe.
Or seeing how a virtual sofa looks in your actual living room on your phone.
Perfect example. You see the virtual object on top of your real view, but typically there's not much interaction, or maybe none at all, between the digital and the physical. The digital info is just superimposed.
So it's layered on, but not really part of the environment.
Exactly. It's static relative to the world. Which brings us to the middle ground, the really interesting part. Mixed reality, or MMR.
This feels like the goal for a lot of applications.
It really is the crucial innovation right now. Because with MR, the digital elements aren't just superimposed, they're fully interactive with the physical environment. Meaning a virtual ball can bounce off your real table, or a digital character can hide behind your actual sofa. The virtual object understands and interacts with the real space.
Like the HoloLens 2.
Microsoft's HoloLens 2 is the classic example, yeah. It truly blurs the line because the virtual content seems to exist within the real space, respecting its geometry, not just pasted on top like a sticker.
Okay, so what's enabling this move across the spectrum?
Yeah.
From basic VR to this really integrated MMR, it can't just be faster processors, right?
No, not at all. It really comes down to fundamental breakthroughs in optics and display technology. That's what's making these devices smaller, lighter, and actually comfortable enough to wear for more than a few minutes.
Optics are key then.
They are the core enabler. They determine everything: how realistic things look, how wide your field of view is, and crucially, comfort. Take VR, for instance. The shift to pancake optics has been a game changer.
Pancake optics. Sounds flat.
Huh. Well, they allow for much flatter headsets. Instead of needing bulky Fresnel lenses, pancake optics use polarized light and folded pathways bouncing light off reflective surfaces to achieve the necessary focal length in a much thinner package.
Ah, so they're folding the light path, like bending it inside the lens assembly.
Exactly. You're essentially compressing maybe, say, a foot of optical path down into just a few centimeters.
Which makes the whole headset dramatically smaller and lighter?
Precisely. Reduces the volume, reduces the weight on your head. That's absolutely vital for user adoption and comfort.
But even with clever tricks like pancake lenses, there's still this fundamental problem that causes eye strain and nausea, right? The divergence accommodation conflict, VAC.
Ah, yes, the VAC. That is the primary enemy for headset designers. It's the main reason people feel visual discomfort or even motion sickness.
Can you walk us through why it happens? What's the engineering challenge there?
Sure. So in the real world, when you look at something, say, nearby, two things happen in your eyes automatically and in sync. Your eyes verge, they turn slightly inward to point directly at the object, and they accommodate the lens inside each eye changes shape to bring that specific object into sharp focus.
And they both adjust to the same distance.
Exactly. If the object is 10 feet away, you verge for 10 feet, you accommodate for 10 feet, your brain expects this link. But in a standard VR or AR headset,
It gets messed up.
The virtual object might look like it's 10 feet away, so your eyes verge for 10 feet, but the actual screen emitting the light, that's maybe only an inch or two from your eyeballs. So your eyes have to accommodate to that very close distance.
Ah, so your vergence says far away, but your accommodation says right here.
Precisely. Your brain gets these conflicting depth cues. Vergence says one thing, accommodation says another. That mismatch is what leads to the fatigue, the eye strain, the nausea. It feels unnatural.
Okay, so how on earth do engineers fix such a fundamental biological mismatch?
Well, it takes some incredibly sophisticated hardware solutions. One approach, especially for higher-end systems, is using light field displays.
Light field.
Yeah, instead of just showing a flat 2D image, a light field display tries to reconstruct the actual rays of light as they would emanate from a real object in 3D space. It's trying to mimic how light behaves naturally.
So your eye just reacts normally.
That's the goal. If you can accurately replicate the light field, your eye's vergence and accommodation responses should naturally align, just like they do in the real world.
But there's always a but.
There's always a but. Right now, light field displays are generally complex, they can be bulky, computationally expensive, and often the resolution isn't quite as high as conventional displays. It's still an evolving area.
Okay. What about for AR specifically?
Right.
Where you need to see the real world through the display, and the device needs to be super lightweight and maybe even look like normal glasses eventually.
Right. For AR, thinness and transparency are critical. That's where things like holographic lenses, or more accurately, holographic optical elements, HOEs, come in.
Like in the HoloLens.
Exactly. Devices like HoloLens 2 rely heavily on HOEs. They aren't projecting holograms in the sci-fi sense. They're essentially very thin, specialized films or waveguides that use the principle of diffraction bending light waves in very precise ways.
How does that help?
They can direct the light from a tiny internal display towards your eye, creating the virtual image, while also allowing the light from the real world to pass through relatively unobstructed. And they do this in a very thin form factor.
So they're lightweight and allow see-through. Any other benefits?
Yes, they can help achieve a wider field of view, FOV, compared to some other compact optical designs, without making the device super thick. Getting that wide FOV is another huge challenge for AR.
Okay, and is there anything that tackles that vergence accommodation conflict more dynamically?
In real time.
Yes, that's where adaptive optics come into play.
Yeah.
This is some of the most advanced stuff.
Okay.
Like systems using varifocal displays. These are displays that can actually change their focal distance on the fly.
They typically work hand in hand with gaze tracking. The headset has sensors that constantly monitor precisely where your eyes are looking, where they're converging.
So it knows what virtual object you're focusing on.
Exactly. So if the system detects your eyes are verging on a virtual object that's meant to be, say, 5 feet away, it actively, mechanically or electronically, adjusts the display's focal plane to also be 5 feet away.
So it forces vergence and accommodation to match again.
Precisely. It dynamically solves the VAC based on your gaze. This kind of real-time adjustment is absolutely critical if you expect professionals to use AR headsets for hours on end for complex tasks. It makes extended use feasible.
Wow. Okay, so we have these amazing optical systems, but they're useless if the virtual content just floats around randomly. The software needs to lock it into the real world somehow.
Absolutely. And that requires moving beyond old methods that needed physical markers. We need robust, markerless AR.
Markerless being the key, because you can't stick QR codes everywhere.
Exactly. If you want AR to work seamlessly in a factory or walking down a city street or in your own messy living room, you can't rely on pre-placed physical markers. It has to understand the environment on its own.
So, how does it do that? How does it map a space it's never seen before and anchor digital content reliably?
The magic behind that is a technology called SLAM. It stands for Simultaneous Localization and Mapping.
Okay, SLAM. Break that down.
So the device, whether it's a fancy headset or just your smartphone, uses its sensors, primarily the camera, but also the gyroscope and accelerometer.
Motion sensors.
Right. It uses all that data to do two things at the same time. It builds a 3D map of the environment it's seeing, identifying surfaces, edges, corners, points of interest.
Okay, mapping.
And simultaneously, it figures out its own precise position and orientation within that map it's building. That's the localization part.
Ah, so it knows where things are and it knows where it is relative to those things.
Exactly. And once it has that map and its location, it can anchor virtual objects to specific features in the real-world map. So if it detects a tabletop, it can place a virtual lamp on the tabletop, and it will stay there even if you move around.
And that persistence is key, right? If you walk away and come back, the virtual lamp is still on the table.
That's the goal of good SLAM systems, yes. Maintaining that persistence and spatial awareness is absolutely critical, not just for fun filters, but especially for serious industrial or professional applications.
Makes sense. If you have virtual instructions floating next to a specific valve on a complex machine.
They have to stay locked to that valve, rock solid, no matter how the mechanic moves their head or walks around the machine. SLAM makes that possible.
And this capability, it's not just in high-end research labs anymore, is it?
Not at all. The real democratization of markerless AR, powered by SLAM, came with the software development kits, the SDKs, from the big players. Specifically, Apple's ARKit and Google's ARCore.
Putting it on phones.
Exactly. Suddenly, sophisticated SLAM capabilities were available to developers targeting hundreds of millions, even billions, of existing smartphones and tablets worldwide. That just ignited the development landscape.
Okay, so this foundation, the optics getting better, SLAM figuring out the world. This is where things take a really serious turn, I think. We move from maybe consumer gadgets or entertainment.
So straight into the heart of industrial operations, these hyper-efficient, high-stakes environments.
Yeah, and AR/VR technology isn't just a nice-to-have here. Sources suggest it's actually becoming critical for this next wave of industry, often called Industry 5.0.
Absolutely. And right at the core of that Industry 5.0 vision is the concept of the digital twin, or DT.
Digital twin. We hear that term a lot. What is it precisely in this context?
So a digital twin isn't just like a 3D model or a blueprint. It's a living, dynamic, digital representation of a physical asset or a process or even an entire system within a smart factory.
Feeling how?
It's constantly fed real-time data from the physical counterpart via IoT sensors, temperature, pressure, vibration, output, energy use, you name it. This creates a virtual mirror that reflects the current state of the real thing.
And what's the point of having this perfect mirror?
It allows for incredible levels of monitoring, control, analysis, and decision support. You can test changes on the twin before risking the physical asset, predict failures before they happen, optimize performance in ways you couldn't before.
And the Industry 5.0 angle here, it's not just about making more stuff faster, is it? The source material really emphasized the sustainability link.
It's deeply intertwined. DTs are seen as absolutely central to hitting sustainability targets because you have this perfect digital replica.
You can experiment safely.
Exactly. Engineers can run countless simulations on the digital twin to optimize energy-hungry processes without wasting a single watt or drop of material in the real world. They can fine-tune parameters to boost energy efficiency, figure out how to use raw materials with maximum effectiveness, minimize waste.
So it directly helps reduce the environmental footprint, greenhouse gases.
Dramatically. The digital optimization becomes a core driver of the green transition in manufacturing.
Okay, but for this digital twin to be effective, to be that perfect mirror, it needs data. Lots and lots of data.
Constantly. A massive, continuous stream. The sources we looked at categorize this data flow into three main types, three crucial streams that feed the twin.
What's the first one?
First is production data. This is everything directly related to the manufacturing process itself. Think about consumption metrics, how much raw material is being used, emission levels, how much waste is being generated.
And the machines themselves.
Yes. Also, crucial equipment status data. What's the current configuration? Is it running? Is it down? Why was it down? Tracking downtime is huge for efficiency.
Okay, production data. What's the second stream?
The second is explicitly energy consumption data. This is vital for that sustainability piece we just talked about.
Tracking the power draw.
Right. Detailed tracking of electricity pulled from the grid, but also, increasingly important, power generated and consumed from on-site renewable sources, like solar panels.
Why separate this from general production data?
Because by linking energy use directly to specific production steps or machine states, you can pinpoint the real energy hogs. Maybe running a certain process overnight uses cheaper grid power, or maybe you can schedule high-load tasks to align perfectly with peak solar generation. It allows for very targeted energy optimization.
Makes sense. And the third data stream, you mentioned it's sometimes overlooked.
Yeah. The third is environmental data, and this covers both the internal factory environment and the external conditions around it.
Internal like.
Temperature on the factory floor, humidity levels, noise, even air quality in specific zones. For some processes, like, say, precision molding or cleanroom work, these factors are critical for quality control.
And external data.
Things like the outside ambient temperature, weather conditions, maybe even local pollen count if it affects air intake filters. If the digital twin sees the external temperature as forecast to spike, it could proactively adjust the internal HVAC system before the sensitive machinery overheats, preventing defects and saving energy compared to just reacting later.
Okay, so you've got this incredible digital replica of the twin, constantly updated by these streams of production, energy, and environmental data. It's processing, analyzing. But Industry 5.0 isn't just about automation, right? It emphasizes human-machine collaboration.
Exactly. It's about blending the strengths of human intuition, creativity, and experience with the analytical power and tireless consistency of machines.
And this is where AR comes back into the picture, as the bridge.
Precisely. AR provides the crucial human-machine interface. It's how the human operator interacts with, understands, and leverages the insights from the digital twin in the context of the physical world.
How does that work in practice? Are there different levels of integration?
Yeah, we can think about it in terms of 3 levels of digital twin maturity and how AR supports each one.
Okay, let's break those down. Level 1.
The simplest level is the passive virtual twin. Here, it's mostly about observation. Data flows from the physical asset to the virtual twin, and AR acts as an enhanced display.
Like a heads-up display for the real world.
Kind of, yeah. An operator looks at a physical pump, and through their AR glasses, they might see a simple overlay showing its current pressure, temperature, and flow rate pulled live from the twin. Or maybe a flashing red alert appears over a valve that's exceeding safety limits. It's basically status monitoring and alerts, but overlaid contextually.
Okay, informative but passive. What's the next step up?
Level 2 is the hybrid subspecies. Now we're moving beyond just observation into active analysis and feedback between the physical and virtual.
So the twin starts doing more thinking.
Right. The system can perform modeling, run predictions, help with diagnosis, suggest optimizations, and AR becomes a much richer tool for interacting with that analysis on site.
Can you give an example?
Sure. Imagine an engineer wearing, say, a HoloLens 2, walks up to a complex machine that's malfunctioning. They look at it. The AR system uses object recognition to identify the specific component that's failing. It pulls the relevant diagnostic data from the digital twin, maybe highlights the faulty part with a virtual glow, and then overlays step-by-step animated repair instructions directly onto the physical machine.
Wow, so it guides the repair visually.
Exactly. The physical inspection and the virtual analysis are working together, mediated by AR.
Okay, that's pretty powerful. What's the ultimate level then? The third one.
That's the cognitive twin. This is the most advanced and, frankly, the most ambitious stage.
Cognitive implies intelligence. Consciousness.
Not consciousness, but certainly a higher level of intelligence and autonomy. The cognitive twin aims to dynamically combine human intelligence, our creativity, our design skills, our ability to handle unforeseen problems with the most advanced machine computation, like deep learning and AI.
So it's a true partnership.
Yes. In this scenario, the human isn't just following instructions to fix a diagnosed fault. They're working with the twin to solve complex, maybe even completely novel and unpredictable situations.
Like what?
Think about a major unexpected disruption in the global supply chain. The cognitive twin could rapidly model dozens of potential responses, rerouting materials, changing production schedules, substituting components, analyze the costs and benefits of each, and present the top few data-backed options to the human operator via AR.
And the human makes the final strategic call.
Exactly. The human brings the strategic thinking, the ethical considerations, the creative problem solving, while the twin provides the immense predictive power and data analysis. It's leveraging the best of both worlds.
Okay, but the second we start talking about cognitive twins, making suggestions about multi-million-dollar production lines fed by real-time data from sensors all over the factory, potentially connected globally, the conversation has to turn to security.
Immediately, it becomes the absolute non-negotiable challenge.
Because if someone compromises that digital twin,
the consequences could be catastrophic. We're talking halted production lines, potentially physical damage to equipment if wrong commands are sent, theft of incredibly valuable intellectual property, compromised safety systems. The stakes are enormous.
so security can't be an afterthought.
Absolutely not. It must be baked in from the very beginning. The principle has to be secure by design. Because these industrial digital twins, or IDTs, handle such sensitive operational and business data, engineers have to proactively hunt for vulnerabilities before the system even goes live.
How do they do that? Hunt for vulnerabilities.
They use established methodologies for threat modeling. One of the most common is called STRIDE. It's an acronym that helps engineers systematically think through the different categories of threats a system might face.
STRIDE. Okay, let's unpack that. What are the key threats we need to worry about with these IDTs?
Right, STRIDE gives us 6 categories. The S is for spoofing.
Impersonation.
Exactly. An attacker is successfully pretending to be a legitimate user, device, or system component. Imagine someone hijacking the login credentials of a remote maintenance engineer.
And sending commands to shut down a critical machine.
Or alters parameters dangerously, yes. The mitigation here is obviously strong authentication.
Multi-factor authentication, MFA, is baseline, maybe biometrics, plus robust encryption for credentials and communication channels. Verifying identity is paramount.
Okay, S is spoofing.
T is for tampering. This means maliciously modifying data or processes.
Changing the data.
Right. Maybe subtly altering sensor readings flowing into the twin so it makes bad decisions, or changing configuration files on a machine tool to make faulty parts, or even tampering with the twin's predictive models.
How do you stop that?
You need strong authorization controls. Who is allowed to change what? Plus, cryptographic techniques like data hashing and digital signatures. If data is tampered with, the signature won't match and the system knows something's wrong. Secure communication protocols are also vital here.
Got it. Spoofing, tampering.
Gosh.
Okay. R stands for repudiation. This is the threat of someone denying they performed an action.
It wasn't me.
Exactly.
Yeah.
In a high-stakes industrial environment, if an operator overrides a critical safety interlock, or if an engineer pushes a risky configuration change, you need an undeniable record of who did it and when.
So, lugs.
Rigorous, comprehensive, and tamper-proof logging and audit trails are the only defense. Every significant action, every command, every data modification needs to be logged securely and traceably.
Okay.
I is for information disclosure. This is basically data leakage, sensitive information getting exposed to unauthorized parties.
Like trade secrets or process parameters?
Or even personal data about workers. This could happen while data is stored at rest or while it's being transmitted in transit. The main defense here is pervasive encryption, encrypting data, both at rest and in transit, using strong, up-to-date cryptographic standards. Secure coding practices are also essential to prevent accidental leaks through software bugs.
Makes sense. 2 left.
D is denial of service, or DOS. This is where the attacker tries to make a system or resource unavailable to legitimate users.
To shut things down.
Right. Maybe by flooding the network connected to the twin with jump traffic, or by infecting a critical control system with malware that crashes it. In Industry 5.0, downtime costs are massive, so this is a huge concern.
Innovation.
Things like robust firewalls, intrusion detection systems, sophisticated anti-malware protection, and crucially, redundancy. Having backup systems and network paths ready to take over instantly if a primary component is attacked.
Okay, finally, E.
E stands for elevation of privilege. This is when an attacker, maybe starting with low-level access, manages to gain higher-level permissions they shouldn't have.
Like a basic user becoming an administrator.
Exactly. Getting root access, admin rights, that allows them to potentially bypass other security controls, tamper with logs, install malware, whatever they want.
And the defense for that?
The core principle here is least privilege. Every user, every application, every system component should only have the absolute minimum permissions necessary to perform its specific legitimate function, nothing more. This needs to be enforced rigorously and audited regularly through access reviews and certifications.
So spoofing, tampering, repudiation, information disclosure, denial of service, elevation of privilege, addressing all 6 of those robustly,
Is essentially the security foundation that makes the whole industrial digital twin concept viable and trustworthy. Without it, the risks are just too high.
Okay, so we've really mapped out this one major direction for AR and related tech. It's powerful, it's complex, it's driving towards industrial efficiency, optimization, security, billions of dollars at stake.
Yeah, that Industry 5.0 path is very clear, very focused on performance and control.
But earlier, you mentioned a counter-narrative, a completely different vision for how this same underlying technology, the spatial mapping, the overlays, the interfaces, could be used, not for industry, but for public good.
That's right. And that brings us to the ideas behind the Paradise Project. It's a fascinating, almost philosophical contrast to the industrial path.
What's the core vision?
Instead of using AR to optimize factories or sell more products, the Paradise Project envisions using accessible AR tools to help communities literally reverse urban decay, specifically by supporting community-led gardening and beautification projects.
So, using AR to help people plant trees and flowers in neglected spaces.
Essentially, yes. But it's framed within a much larger goal of fostering ethical, non-extractive, regenerative policies at the local level.
Non-extractive, that sounds important. What does that mean in this context?
It's central to their whole philosophy, which they summarize as ethical, not extractive.
Yeah.
It signifies a fundamental break from typical tech deployment models. Non-extractive means the community isn't just a passive user or a source of data to be mined. They are active co-creators in the entire process.
The community drives it.
Yes. And crucially, it mandates data sovereignty. Any data generated like a 3D scan of a vacant lot before work starts, or the collective design ideas for the garden, that data is owned by the community, not by some tech company headquartered thousands of miles away.
That's a huge difference from how things usually work.
A massive difference.
Yeah.
And the ultimate goal is always tangible: physical change, actual green spaces, improved biodiversity, community gathering spots. The AR technology is just seen as a temporary tool, a scaffold for reality, to help achieve that physical outcome.
Okay, so how does it work practically? How do you go from a digital idea to an actual garden using AR? The project outlines a specific method, doesn't it?
It does. They call it the phased greening methodology. It's designed to be practical and accessible, moving the project from concept to reality in 3 stages.
Stage 1.
Phase 1 is visioneering. This is all about collaborative design and building buy-in. Community members use readily available AR, probably just on their smartphones or tablets.
So accessible tech.
Right. They use it to overlay potential designs onto actual vacant lots or neglected corners in their neighborhood. They can see, okay, what would a small orchard look like here? Where could we put benches? How big would that community vegetable patch be?
So everyone can visualize the potential together.
Exactly. It makes the abstract idea tangible. It helps build consensus, get people excited, and secure that crucial emotional investment before anyone picks up a shovel or spends any money. Makes the shared dream feel real.
Okay. Visioneering gets the plan. Phase 2.
Phase 2 moves into the actual work, guided installation.
This is where AR becomes a tool for doing, not just seeing.
Precisely. The AR overlays shift from being design mock-ups to being practical guides for action. When the community gathers to build the garden, the app, using that SLAM tech we talked about,
Maps the real ground.
and projects precise digital outlines onto it. It might show exactly where the perimeter of a raised bed needs to be built. Or it could project little markers showing the precise spacing and depth needed for planting specific shrubs or trees according to the plan.
So it helps ensure things are built correctly, even by volunteers who aren't expert gardeners or landscapers.
Exactly. It democratizes the skills needed. Novices can execute potentially complex designs with accuracy, following the AR guides. It could even show things like watering schedules or pruning guides later on.
Clever. Okay, visioneering, guided installation. What's phase 3?
Phase 3 is about making the impact last and embedding the story. living memory and storytelling.
Living memory.
Yeah, this uses persistent, location-based AR to attach the garden's history, its creation story, and its ongoing meaning directly to the physical place itself.
How would that work?
Imagine you visit a thriving community garden a few years after it was built. You hold up your phone or AR device, point it at the garden, and the AR layer could display information linked to that spot. Maybe a time-lapse video showing the transformation from vacant lot to green oasis.
Or the names of the people who designed and built it.
Exactly. Or stories from elders about what the space used to be. It creates this persistent digital layer of shared heritage, community pride, and collective memory. It elevates the garden beyond just being plants. It becomes a living archive of community action.
That's a really lovely idea. Now, this sounds like a grassroots, community-focused initiative, but the project seems to have bigger ambitions, too, linking itself to global organizations like UNESCO.
Yes, that's a very strategic part of their approach. By aligning the project with major international policy frameworks, especially those from UNESCO, they aim to gain legitimacy, scalability, and ensure the project is grounded in established ethical principles, not just, feel-good local efforts.
Which frameworks are they citing?
They explicitly connect their work to the UNESCO recommendation on the ethics of artificial intelligence from 2021, which stresses human-centered AI. Also, the 2005 Convention on the Protection and Promotion of the Diversity of Cultural Expressions, and, of course, key UN Sustainable Development Goals, particularly SDG 11 on sustainable cities and communities, and SDG 17 on partnerships for the goals.
So they're embedding it in existing global efforts for sustainability and cultural heritage.
Exactly. It frames the project not just as gardening, but as contributing to recognize global priorities.
And part of this global vision involves creating a digital seed bank. What's that about?
This is a really interesting and ambitious proposal. The idea is to establish a global, open-access digital repository, perhaps under UNESCO's guidance. But instead of storing physical seeds,
It stores digital ones,
Well,
3D models.
precisely, culturally relevant and ecologically appropriate 3D models of plants, trees, maybe even local architectural elements or culturally significant designs.
Why is that needed? Why not just use standard 3D model libraries?
To counteract what they call digital colonialism. Imagine a community in, say, a high-altitude desert region wants to use the Paradise Project tools. If the only available 3D plant models in the standard AR library are like generic palm trees and lush tropical flowers.
It's completely irrelevant and inappropriate for their environment and culture.
Exactly. The digital seed bank aims to provide a diverse, curated collection of virtual assets that are actually suitable for different biomes and cultural contexts worldwide. So the virtual designs can accurately reflect local reality and aspirations. It ensures the digital tools serve local needs rather than imposing external aesthetics.
That makes a lot of sense. Okay, so the Paradise Project presents this very positive, ethical application of AR.
Yeah.
But even with the best intentions, deploying persistent AR layers in public spaces, it must raise some tricky ethical questions itself, right?
Oh, absolutely. Even a project focused on good has to grapple with the inherent ethical risks of pervasive AR technology. The potential for misuse is always there.
Like what kind of risks?
One major area of concern discussed in the sources is AR annotations. This is the potential for people to layer digital information onto public places, objects, or even other people without consent or in ways that are misleading or harmful.
Like digital graffiti that only AR users can see.
Sort of, but potentially much more insidious. Imagine false or defamatory information being digitally attached to someone's home, or a business getting tagged with fake negative reviews that appear overlaid on their storefront in AR.
And unlike website content, this digital layer is tied to the physical location, harder to control or take down.
Much harder. It creates the possibility of fixed, persistent, potentially damaging digital reputations being attached to physical reality, with complex questions about moderation and control.
Which leads directly into this wider debate about our rights in a world filled with digital overlays. The sources mentioned perceptual rights.
Yes, this is a really thorny emerging area. The debate is framed around two competing concepts: perceptual agency and perceptual autonomy.
Agency versus autonomy. What's the difference?
Perceptual agency is essentially the right to create and deploy AR augmentations into the world. Your freedom of digital expression, you could say, the right to put your virtual layer out there.
Okay, my right to augment.
Right. But perceptual autonomy is the flip side. It's your right to control what augmentations you perceive in your own surroundings. Your right to filter out unwanted layers, to reject digital content you don't consent to seeing overlaid on your reality.
Ah, so my right not to see your augmentation if I don't want to.
Exactly. And you can immediately see the potential conflict. My right to express myself digitally might clash with your right to control your own perception of reality,
Especially in public spaces.
especially in public spaces. And the definition of what's considered an acceptable augmentation is going to vary wildly based on location, culture, context. What's perfectly fine in a bustling commercial district might be deeply offensive or inappropriate if overlaid onto a place of worship, a historical monument, or a private residence. Resolving these conflicts over perceptual rights is going to be a massive legal, ethical, and cultural challenge as AR becomes more common. Hashtag #ITRO.
Wow. Okay, so we've really journeyed through the engine room of extended reality today. And it feels like we've uncovered these two really powerful, almost competing paths emerging from the same technological core.
Yeah, they really are divergent. On one side, you have that intense focus on efficiency, security, bottom line profitability. That's the world of Industry 5.0.
Where the secure digital twins, using all that advanced optics and SLAM we talked about, are optimizing every last drop of energy, every manufacturing step, guarded by defenses against things like spoofing and tampering.
It's a vision of control, optimization, and security. Highly engineered, highly managed.
But then there's this other path, the one exemplified by something like the Paradise Project.
Right, using the exact same foundational the SLAM algorithms mapping the vacant lot, the lightweight optics in a smartphone displaying the design, but using it as, well, an ethical scaffold for reality.
Focus completely differently. Community empowerment, owning your own data, physical regeneration of neglected spaces.
It reframes the technology not as a tool for extraction or control, but as a potential tool for healing and connection.
And the underlying tech itself. You know, the pancake optics making VR sleeker, the adaptive optics finally tackling the VAC for comfortable AR, the SDKs like RKit and RCore putting markerless AR in everyone's pocket. It feels like widespread adoption is becoming, well, almost inevitable now.
The technological barriers are falling rapidly. Persistent AR and XR experiences, whether first on the factory floor or overlaid onto our city streets and homes, they are coming. The capability is arriving.
Which leaves us with a pretty critical question, doesn't it?
It really does. Which of these paths, or what blend of them, will ultimately define our future relationship with this increasingly blended digital and physical world?
Will the incredible power of persistent, context-aware AR be used primarily to secure industrial secrets, maximize online retail conversions, maybe provide ever more sophisticated digital entertainment and escape?
Or will we, as a society, consciously choose to harness this same power as a tool? A tool to perhaps finally start healing our damaged urban landscapes, reconnecting communities, and maybe, just maybe, rebuilding some kind of common paradise, brick by digital brick, flower by physical flower.
The technology itself might be neutral, but its application definitely won't.
Exactly. And ultimately, it's up to all of us, isn't it? As users, as designers, as policymakers, as citizens, we get to decide which story this augmented world we're building is going to tell.